Hi everyone, welcome back. So let's talk about dew point temperature, which honestly for a lot of these subjects is probably the one that you're going to understand the best just intrinsically, because you've seen this, you've felt it, because at some point everybody's had water on the outside of a cold glass. So what is dew point temperature? Well, it's simply the temperature at which condensation will begin. And it says if cooled at constant pressure, we're assuming that the pressure outside of us is more or less constant. So here it is. Our temperature entropy diagram. Here's our curves. At this point right here, we are a saturated vapor. As we go from here to here, we begin to condense. So when the temperature of the air drops, and it drops down to this point, the water in that air will begin to condense. That's what we're getting at here. And so the temperature for our dew point is the same as the saturation temperature at that partial pressure for our vapor. Remember, we're not talking about the pressure of the air. We're not saying 1 atmosphere here. We're saying what is the partial pressure of the water vapor in the air, okay? What's that partial pressure of that water vapor in the air? And so once we reach the temperature, the saturation temperature for that pressure, we'll begin to condense. Okay, so here's a cold drink, soda. Quenches your thirst. And there's moist air outside of it. If it's perfectly dry air, we won't have any condensation. No issues there. But if the soda is cold, colder than the air for one, and also colder than the dew point of the water in the air, the vapor in the air, then you will begin to see liquid water droplets. That's not because water is going out of the soda can, it's because water is coming out of the air onto the soda can. And this is a way that you can actually get water out of moist air. You can either dehumidify your home using this, or you can, if you're in the desert, get water out of the air to drink. Okay, another place you might see this is fogging of the windows in your house. So if you look in your house, you don't see just fogging anywhere. It's typically at the windows. And the reason for that is because your house typically follows a temperature distribution. In the middle, it's nice and whatever your room temperature is, and towards the windows, it's going to be either hotter or colder depending on the day. We're going with a cold outdoor day, and so it's going to be colder at the windows. That's where you lose a lot of heat in your house. And so it's going to cause it to condense. We're going to see water beginning to condense on the inside of the window. If you have very good insulation, like if you have very good windows, this drop right here might be a lot less. You might not see as much condensation. And hopefully you're not seeing condensation inside your windows, because that's not a good thing. Okay, so we're going to see right now, just do a really quick example before we do our real example after a moment. At what temperature, would we see condensation at this temperature? My bad. And we have 75% relative humidity. Relative humidity, remember, that is me saying that the air is holding 75% as much water as it possibly can. Okay, it still has some more room. It can hold more, but it's at 75% of the max. So first off, we need to figure out what is the dew point for our air, for the water vapor in our air. And so that'd be the saturation temperature at the partial pressure of the water vapor. Well, what is that partial pressure of the water vapor? It's not that hard to get because our relative humidity is actually a ratio of pressures. We saw this a while ago. It's equal to the partial pressure of the vapor over the saturation. This is the max it could possibly have, and this is what it actually has. The more water there is, you can kind of think of it pushing harder on everything around it. So we're at 75% of our max, okay? 75% of our max. And we're saying that the air is at 20 degrees Celsius. That's the stuff that's going to be, we're talking as our baseline. So we're wondering where this pressure was chosen from. That's because we're using the 20 degrees Celsius. So we do this, and we can see that the partial pressure for our water vapor is very, very low because our air isn't mostly water vapor. It's only a small portion of its water vapor. It's a lot of other things instead. So now, using that, we can then say, okay, what is our saturation temperature at this pressure? Now, if you're actually looking at your tables, you're most likely going to have to interpolate. I'm sorry to say that. You're not going to be able to find 1.754 perfectly in your tables. But by interpolation, we can figure out that the dew point temperature will be 15.4 degrees Celsius. This is me going to the tables, seeing the temperature and the pressures, and specific volumes, internal energies going down the line. And I'm saying, okay, I know this now. I go down until I get as close to I can, and then I look over and say, what's the temperature? Okay, this is my saturated mixture tables. You've seen me do problems with that a lot in the past, but if you need that, leave a comment and I can go add a extra video going back to those tables again. So the dew point temperature is 15.4 degrees Celsius. My temperature inside the house at the windows is 16 degrees Celsius. So the answer to this question, will I start to see moisture condensing on the inside of my window, is no, I will not, because my window is warmer than the outside, than the dew point. And because it is warmer, it's not going to begin to condense. If it got colder outside and my windows dropped to 15 degrees Celsius, I would begin to see condensation. Okay, so with that, let's try out another problem here. So this happens to everybody. Everybody's done this at some point. You open a refrigerator, you pull out a cool canned drink, bottle drink, whatever your drink is. And it's at 40 degrees Fahrenheit. Yes, I'm sorry, we're in English units. And we're going to determine the dew point temperature of room at 10 degrees Fahrenheit and 39% relative humidity. And also we're going to figure out, will my can begin to sweat? Okay, will it start to sweat? Will I see condensation on the outside? So first off, let's draw a pretty picture. Cherry Coke. This was my jam when I was younger. My goodness. I think it's because my dad took me out to get a soft drink one time from a machine when I was like 5 years old, and this was the drink. And so it's been my drink ever since then. Okay, now let's calculate our vapor pressure. So we have the temperature of the air in the room. We also have its relative humidity. These are the two things we're going to need. So first, we're going to use that temperature to find out what is my saturation pressure at 70 degrees Fahrenheit. It's a nice round number. You should be able to find it in the tables really easily. Once you've gotten that, which is 0.3633 psi, I'm going to then multiply that by my relative humidity because, yes, this is if I had 100% as much vapor as it can possibly hold. And instead, I only have 39% of that. So my vapor pressure is 0.1417 psi. Okay, so we've gotten our vapor pressure now. Now we're going to use this to go back to those tables and say, okay, what is the saturation temperature at this pressure? So if I do some interpolation, what I find is that for 0.1417 psi, the saturation temperature would be 43.8 degrees Fahrenheit. And you know what? Let's go ahead and see this real quick. Let's go ahead and see this. I want to jump to the tables so that you can all get a taste of what that looks like. Okay, so here we are at the tables. This is Appendix 2 in our textbook because this is the English units. You can find this online for various liquids. So if you don't have this textbook, go check there. I have to get questions about this, so I'll go ahead and show it real quick, what textbook it is. Let's see. Will it do it right if I do this? I'm hoping it will. Front matter. It's Thermodynamics Engineering Approach, 10th edition by Yannis Singel. And Yannis, if you're watching this and I pronounce your name horribly wrong, I apologize. It's a great textbook. I like it a lot. Okay, Appendix 2. Back to it. Sorry. So what we're going to do is we have a pressure, and we're going to go there and find the temperature using that pressure. So I jumped here, and it jumped to superheated for some reason. And there we go. What we're going to find if I go really, really low is it goes down to 1. I have 1 and 2 right here. And just checking real quick, my pressure I need is 0.1417. So this is not going to be very helpful to go to the pressure table. You're like, well, the values don't go low enough. What am I going to do? Check the temperature table. Remember, these two columns are just interchangeable. So there's nothing really special about them. Just where do you have nice round numbers? So if I go over here, okay, you can see here's my temperatures, here's my pressure. I can still match these up. And so I'm at 0.1417. It's in between these two. And so what I have to do is interpolate. So I would interpolate between these two values to figure out my temperature, which will be between these two values. And since it's closer, like 0.1417, I would say it's about like 44, which isn't too far off. So back to our PowerPoint now. Now you've seen it in the tables, how you find these values. Okay, and here we are, back in it. So the question now is, will the can sweat? Okay, will this can sweat? And the answer is yes, it will sweat because it's at 40 degrees Fahrenheit, and that is less than 43.8 degrees Fahrenheit. This is the dew point temperature. My can is colder than that. The air surrounding it will begin to release the water, and it will begin to sweat on the can. So there you go. You got a little extra tidbit there. We got to see the tables. Hopefully this helps you, and I'll see you all next time. Bye-bye.